All right, this is where you're actually going to start learning something. The rest, was there, but it wasn't. It's like, that was kindergarten. Now we're moving up to first grade. Okay, let's start talking about this stuff. All right. What if I asked you what the combination of the following numbers would equal 113? Could we figure that out? How would we do that? What would the process be? How would you figure out which combination equals 113? Add some together. Add a couple together, and that's too many. Take this one, and so you would try to figure it out. Is that a hard problem to do?
We'll go for trial and error method.
That's trial and error. So it's not very hard, but it is considered a hard problem because if you had 200 digits to work with, and the total was billions, you could see how it would take you a long time to figure out the right combination, okay? Well, we're going to talk a whole bunch more about that here in a little bit, okay? But it's not really that it's hard, but it is hard, okay? Oh, this stinking thing drives me crazy. Okay. There's 3 classes of problems up there. Guaranteed to be on at least 2 of your tests, okay? Guaranteed. These will be on there. So let's talk about what these are. First of all, we have what's called a P problem. It's a polynomial. It's a problem based on polynomial functions. Now, if you have any questions about the math involved, talk to him. He teaches math. I don't. Okay. What it basically says is a set of problems whose solution run in time bounded by polynomial functions of the size of the problem. What the heck does that mean? The longer the problem, the longer it's going to take. It's like if you got a smaller number, it would take a lot less time to figure out. But if I gave you more numbers, it would take longer to figure out. Okay? It says a set of problems that are easy to solve. It just could take trial and error. It could take you a while. Okay? Can be solved in polynomial time. So what the heck does that mean? Basically, it's an amount of time that's roughly proportional to the size of the problem's description. I'll give you an example here. Okay? So if I told you to multiply 2 numbers together, hard or simple? Pretty simple. So basically, the problem itself is very small, so the amount of time it's going to take to solve it for most people will be very small. Hopefully people can do basic math. Okay. Hope so. Okay. How about if I tell you to search for a book from a box of books? Could you do it? If I give you a box of books, could you go through there and find a book? What if I tell you to go through the entire Library of Congress looking for a book? Is it hard? It's not difficult, but it could take you forever. You understand that? I said if I told you to go find a specific book in Rose State's library, it would take less time than the Library of Congress because we have a lot less books. So it's not that it's a hard problem, but the time that it takes to solve is based on the size of the problem. Okay? Like I have a shed in my backyard full of boxes of stuff. I know there's stuff in those boxes, but I don't know where. So it's like whenever I need something out of those boxes, it's like, do I want to spend the time going through those boxes? So I never do, so I never get what I want. I just go and buy something new. So I end up with a bunch of boxes in the shed still. Same kind of thing. It's not hard to do. It just could take a long time depending on how many boxes you have to go through. Okay? So that's a P problem. Okay? Now, NP is considered non-deterministic polynomial. Okay? It's a set of problems whose solutions run in time bounded by polynomial functions of the size of the problem, assuming the ability to guess correctly or guess perfectly. So if I told you to go find the book in the Library of Congress, and you said, I'm going to go on floor number 5, shelf number 2, and grab the 3rd book, and it happened to be the right book. Assuming you can guess correctly, it's easy to do. Okay? Here it goes. It stands for non-deterministic polynomial, where non-deterministic is a fancy way of talking about guessing to test whether it's correct or not. So if I guess floor 5, shelf 2, book number 3 in the Library of Congress, could I walk up to floor 5, shelf 2, book number 3 and check it? Sure, very easily. Same like in math. I got an A in algebra. So many people have a hard time, but math, isn't there pretty much an answer? it's concrete. It's like there is a correct answer. It's not like English where, well, you could have put a comma there, a capital letter there. I just think math is so much easier. Okay, so again, assuming that we can guess correctly, okay, assuming that we can also test it. We need to be able, with NP, we need to be able to test that it works, okay, so it's not worrying about how hard it is. It says problems in NP are still relatively easy as long as you can guess and test the correct answer, okay. It's NP complete if we can verify it quickly. I picked that certain shelf in that certain room, that certain book, and I checked it. Sure enough, the ISBN's matched, so we have the correct book. Mathematical function, I guess x is 3. I put x is 3 into the formula, and the answer comes out correctly, so I can test it. That's what we're talking about, okay? So it says the problem is incomplete if answers can be verified quickly, and an algorithm to do it can be figured out, okay? So we got P and NP complete so far. Okay. All of these are going to be on tests. At least 2 tests. EXP. Set of problems whose solution run time bounded by exponential functions of the size of the problem. You all know what exponents are? Like 2 to the third is 8. 2 times 2 times 2. It's not difficult, but the numbers can get very large very fast. Okay? So an EXP problem says a set of problems whose solutions run time is bounded by exponential functions. Exponents is the way to go. Most of the stuff we work with encryption is using exponents. Okay? Alright. So, the results are basically P problems can be NP problems, which can be EXP problems. Basically, that's a subset or equal to. Just because it's NP complete doesn't mean it's huge. Okay, so if I said x plus 2 equals 5, and I guessed 3, that's really a P problem. It's also an NP complete because I guessed 3, and I can test it, verify that it's true. Or if I said 2 to the something equals 8. Again, I guessed 3, so I can test it, so it's NP complete, but an exponent problem. So you see how they're kind of like subsets of each other. Okay? All right, so NP complete does not guarantee that there's no solution shorter than exponential. In other words, it could take you a very long time to solve these. And the whole point of encryption is that it does take a long time. If you can guess the answer instantly, that's not a good encryption algorithm. I mean, what? It suck. AES takes 149 trillion years to solve. Pretty good compared to the Veneer cipher? Or the Caesar cipher, or any of those? Yeah, a little bit better. Okay. Okay, every NP complete problem has a solution that runs in time proportional with 2 to the n. In other words, as long as it's somewhat small, it's still doable. Okay. This is non-deterministic, can be modeled by threads. You all know what a thread is? I think I've talked about it in a couple of classes. If you don't know what a thread is, I'll explain it again. Kind of like a computer, it can do multiple things. When we do password breaking, we can actually break hundreds and millions of passwords per second. We can actually work on multiple passwords at the same time. I had to write a program when I was in the University of Tulsa that captured network traffic, had to analyze it, and output the results. So that's what I did. I wrote a program that listened on the network, captured the traffic, analyzed it, then output the results. Failed miserably. Does anyone know why? Because I captured it, but while I was analyzing, what was happening on the network? More traffic was zooming by. Because I was like, oh, I got some. Here, let me go look at it. But while I'm looking at it, there's traffic zooming by. So what I had to do is I had to rewrite my program to use threads. So I had one component that all it did was capture traffic. And put it into a vector I think I used. Then another thread just kept looking at that and analyzing it. And when it was done with it, it dumped it in another file. Then another thread that kept outputting the results. So it's kind of like I had 3 people doing it at one time. So that's what we're talking about here. Non-deterministic can be modeled by threads. In other words, we can do multiple things at one time, make this thing a lot easier. So rather than just checking one book, maybe I could, get all of us together, all looking through boxes at the same time, find whatever we're looking for faster. Okay. All right. It says interceptors may use other information to simplify it. You all heard of social engineering? Using what we can guess about people or know about people. You can expect that people trying to break your system are going to use everything they possibly can. Okay? Every technique they can think of to get in. Okay? In some of the classes, we use a program called Metasploit. And whenever heard of Metasploit, someone should have. What Metasploit is a program written by H.D. Moore. It is a database of vulnerabilities. He wrote this program. It works great. He wrote a program that has a database of vulnerabilities, and then you can check your system against it. So I could run this program against this machine right here. Say, okay, I'm running Windows 7 Professional, update level such and such, and this program knows all the vulnerabilities, so it can check and make sure every vulnerability has been patched. So is that a good or a bad program? It's really used to test security. Because his program gets all the updates, he knows what should be patched, and then he's just verifying they were done. But what if you didn't patch your system and someone gets a hold of that program? Can they use it to break into your system? Sure they can. We actually do projects with it. He's calling me from Oklahoma. Who would that be? All right. Okay, now let's talk about hard problems. Okay, some problems are hard to solve. Caesar cipher is not hard to solve. Some of you might think it's hard to solve, but it's not. Okay? This is no polynomial time algorithm is known. Okay? It says a hard problem such as machine scheduling, bin packing. So let's talk about what the heck bin packing is. Okay? I got a bunch of bins. I'm going to fill them. I got a bunch of stuff that needs to go in these bins. What combination of items would fill the bins up perfectly full? You see how that could take a long time to figure out? Kind of like at the beginning, what combination of those numbers equaled 113? Well, it was actually the first two and the last two. But, so it could be hard. Okay, that's what we're talking about here. So is it bad to have hard problems? No, we want to have hard problems. We want it so people just can't guess the answer and get into our stuff. Okay? Is anyone here who's running WEP at home still? Wired Equivalency Protocol? I mean, that's the name of it. Wired Equivalency Protocol. It was supposed to give us the same security as a wire. No, it literally takes 4 or 5 seconds to break WEP. But when it was originally made, it was good. Like the Caesar cipher or the Veneer cipher. When it was first made, wow, this is amazing. But then 300 years, who broke it? Koziski, a Prussian major in 1863, figured out a way to break it. So, things change. It says, data encryption relies on difficult to solve problems. So these are going to get harder and harder. Okay. Okay, secure encryption systems. Says modern techniques are based on hard problems. That's what we talked about. Ones that we can use an algorithm for, ones that we can test to make sure they work, so they're NP complete. Folks, heuristic searching. In other words, there could be lots of choices. We want AES to have so many possibilities that it's going to take you 149 trillion years to check them all. If we used AES and you could check it in 5 minutes, I mean, that's no good. So that's what we're saying. We want something that's super huge and hard to figure out. Okay. So let's talk about some of the different encryption systems. We have public key encryption. Okay. So is that symmetric or asymmetric? Anybody? What do you think? Asymmetric. It's asymmetric. Good, because we have 2 keys. We have a public and a private key. Remember, symmetric is same key, 1 key. This is 2 keys. Okay. 1976, we had Diffie-Hellman, which we are going to cover in this class. Okay. 1978, Merkle-Hellman knapsack, we're starting to cover today. Okay. RSA we'll cover soon, 1978. Then we got Elgamal digital signatures, and we got hashing algorithms. There's just all kinds of them. Okay. We're going to cover a lot more than this. Okay. Let's talk about satisfiability first. This all pertains to the knapsack. Okay. You don't really need to know this for the test, but I'm going to explain it to you. So if I tell you to pick V1, V2, and V3, such that V1 and V1 or V3 and not V3 or V1 is true, have any clue what the heck I just said. In other words, pick the combination of numbers to make our knapsack full. That's all it is. When we looked at that number on the very first slide, remember I told you these numbers? So, did I need the first one and the last one? Yes. But did I need the middle one? No. So, in other words, what combination of numbers would make the answer true? And for that case, the answer would have to be 113. Okay? The knapsack says pick V1, 2, and 3 with either 0 or 1 such that V1 times A1, now let me explain what that means. Okay? What happens when you multiply a number times 0?
0.
So on that first slide, remember we had those 5 numbers. So the first number multiplied times 1. Okay? That's the same number then. Plus the second number times 1. Plus the third number times 0, since you don't need that one. See what I'm doing? Okay? So this is how the knapsack works. Which one should we work? We're going to go into a whole bunch more on this. Okay? We're going to do a whole bunch more. Okay? Just don't freak out yet. We're going to show you how it works. I'm just giving you a little insight of what it is. Okay, so symmetric, we know a secret key, same key. One key for encryption, one key for decryption. Okay? So the encryption key is the same as the decryption key, so either one is considered the key. I have some issues with it. I have key management's an issue. Okay? Again, if Cameron loses his key, what happens to my key? It's the same key. They're both compromised. Okay? So I encrypt with one, decrypt with the same key, get my plain text back. One key per channel. Again, know that math right there. We talked about that 2 times ago, I think. That's the number of keys. You will see that positively on the test. So again, if you ever want to know what's on tests, watch these recordings because I've put them on there. Okay. Now public key or asymmetric. Okay. Separate keys for encryption and decryption. We still have some problems. Okay. So we got me and Cameron talking. Okay. So I choose mine to be the secret key, and his to be the public key, or whatever, okay? So we're good as long as it stays that way. But if I lose the secret key, well then we got a problem as well, okay? So I encrypt with one, decrypt with another. So far so good, everybody understand how to read that, okay? But could I also encrypt with the decryption key and decrypt with the encryption key? Actually you can't, it doesn't matter. As long as you stay the same. As long as you don't keep swapping. Like you cannot encrypt with the decryption key and decrypt with the decryption key. That's the same key. You have to use 2 different keys. They come in a pair. Okay? We will do a whole bunch more with that. Again, know that math. 2N. Positively on, I think, every single test. That third bullet and that third bullet. So know that. Alright. So. Public key or asymmetric, and we have a pair of keys, a public and a private. It really doesn't matter which one's which as long as when I label one public and one private, I keep it that way. I can't keep swapping them. If I swap them, and if I publish one key on the internet, the next week I decide to swap them, publish the other key on the internet, well now both keys are on the internet. I mean they're no longer a private key, so you can't do that. Okay? Alright, the same thing I said. One's kept secret, one's not. I encrypt with one, decrypt with a different, so, you know, easy enough there. Nothing new there. It's just a different way of representing it. Okay? Now let's talk about Merkle-Hellman. We're going to talk a little bit about it today and a whole bunch more next time. This is just to get you starting to think about it. Okay? 1978. Okay? This is encodes the binary message. That's very critical for this one. Only encodes binary messages. But binary can be very easily converted to hex or octal or ASCII or whatever, so it's not an issue. I told you before, my stepson literally writes messages on the board in binary now. And I have to sit there and figure, what did he write? You know, so. Okay. So encode a binary message as a solution to the problem. It's NP complete, okay, because we can test it and make sure it works. Okay. There's something called a simple knapsack, something called a hard knapsack, and it is one-way encryption. Yes, there's some test questions off that slide, particularly the bottom question, bottom slide. Okay, let's talk about the simple knapsack and the hard knapsack. There's actually questions on both of those as well, but a little bit different. Okay, so here's how the knapsack works. Okay, given a set of numbers, like on the very first slide, given those 5 numbers and a target, that 113. So given those, find a set of V's or a set of numbers to multiply those by, where when you add them all up, they equal the target. In other words, add the first 2 and the last 2 by 1 each, add them all up, and multiply times 1 each, and multiply the middle one times 0, and you agree that that will come out with the target. Everybody has to understand that, because if you don't, it's going to be an issue. Actually, let me go back to that slide real quick. We can come forward again, it's not a problem. Okay, so if I was to take 5 times 1, we get what?
5.
I know this is difficult. I'm going to bring up Notepad here, because you have to do this, okay? All right, so if I did, let me change my font so we can actually see it. Format font. Let's go to 20. All right, so 5 times 1 is what? 5. Man, you guys are good. Okay, 7 times 1 equals 7. 15 times 0 equals 0. Then 32 times 1 equals 32. 32. And 69 times 1 equals 69. So we had to figure out the V's. The V's are the ones in the zeros. Okay? We had to figure out the V's to multiply times the S's. The S's are, consider these numbers here a simple knapsack. We had to figure out the V's to multiply the S's by to get the sum. Everybody see that? So our V's are 1, 1, 0, 1, 1. Does everybody see that? Okay? Because you have to know this. Okay? So when I add them all up, I get 113. If I was to change some of those, it wouldn't equal 113. And we're going to learn about a super increasing knapsack, because that is really the only way you can use those numbers to equal 113. If you change them around in any way, you're not going to get 113. So that is the only set of V's that will make this one work. Okay? Okay. So choose the set of V's. When we multiply V times A, in other words, V1 times A1, V2 times A2, V3 times A3, all the way up to whatever number we got. So when it says V to the n, A to the n, that could be V200 times A200, V600 times A600. You know, it's just a variable. Okay. Again, V's come from the set of 0 or 1, just like we did, such that when I multiply them with our S's, we get our target sum of 113. That's all it means. It's not hard to do, because there's only 5 numbers. But what if our target was 2,869,000,000, blah, blah, some huge number, and the number of S's we had was 500 of them? You could see how it would be, I mean, trial and error, you could do it.
So just 2 to the n?
Yes, pretty much, yes. It could literally take the size of the problem, however big it is. Okay, so here's our example. 9, 5, 3, and 12, our target sum is 24. So, what combination of 9, 5, 2, and 13, I said something different a second ago. Oh, what combination of 9, 5, 2, and 13 would equal 24? So it will be 9, 2, and 13. Everybody see that? So our V would be 1, 0, 1, 1. Okay?
Your V's will always only be a 0 or 1?
A 0 or 1 only. Yes, sir.
And V's, can you only have 1 0?
Oh, you can have multiple.
Okay.
Yeah, maybe our target was 22. We could have 1, 0, 0, 1. Oh yeah, it could actually, I don't think it could be all zeros, that'd be 0. But yeah, you could have more than 1, you could have all 1s. So very easily. You know, if our target was 29, it would be 1, 1, 1, 1. So yeah, from the subset of 0 or 1. So we want this so that the sum of a to the I times v to the I, in other words, a1 times v1 plus a2 times v2 plus a3 times v3, so on and so forth, equals 24 in this case. Okay? So it's 9 times 1, 5 times 0 times 2, or plus 2 times 1, so on and so forth, equals 24. Easy enough to do. Set P complete because we were able to guess v. Again, we only were able to guess it because it was a very small problem. If it was huge, no, it's too much work. Okay? And for this problem, there's normally 200 digits, so it's very large. But for the test, I think there's only going to be 4. It'd be a little bit easier to solve if there was only 4. Okay? All right, now let's talk about our knapsack. Our knapsack is that first group of numbers. Okay, it's these right here, this 9, 5, 2, and 13. That's called a simple super increasing knapsack. Okay? What the heck does that mean? Well, it says basically every number is greater than the sum of all the prior numbers. So, 1 is our first number, so obviously it's the greatest number. Then 2 is greater than 1. Then 5 is greater than 2 plus 1. And 13 is greater than 5 plus 2 plus 1.
So that previous one would not be super increasing that.
Was it? I didn't notice. Let's see. Correct, this is not. Right. And the reason it has to be super increasing is if it's not simple super increasing, there could be 2 different sets of v's that make the answer work. Like we know this one's 1, 0, 1, 1. But what if 1, 0, 0, 1 also solved it? Or 1, 0, whatever. In other words, we need it so there's only one answer. Can you imagine if there's 2 different keys for something? That wouldn't be good. We only want one key. Okay, so simple super increasing. I'm going to give you some on the test. You get to pick the ones that are. So again, the 2 is bigger than the 1. The 5 is bigger than the 2 prior. The 13 is bigger than the 3 prior. So on and so forth. Okay? Another way is a sequence of A to the I is called simple super increasing as long as it meets that mathematical formula. In other words, what I just told you. Okay? That basically says the sum and a bunch of other stuff that I don't remember. I'm not a math guy, so it's okay. That's his job. So it's all right. So far so good? Get a general idea how this thing's going to work? Okay. I think that's the end. Okay, now what I'm not covering any more tonight. We're going to cover a whole bunch next time. But if you want to, the next set of slides are already up there. You can go look at them to get an idea. We're going to walk through exactly how this whole thing works and how to solve it and all that stuff. You won't have to write a program to do it. You will have to do homework in it. Now this is, I think, the first assignment where you're actually going to be submitting the homework into the quizzes area. It's not timed. It's set to go on indefinitely. So you can open it, print it off, work on it, just keep hitting save. When you're finally done, you hit submit. Okay? In case if I don't tell you that, that's how it works.
So if there was a 9 between that 5 and the 13, then that would not be...
Well, if we had a 9 here between the 5 and the 13, so it would be 5, 6, 7, 8. 9's bigger than 8. But is 13 bigger than 9 and 5 and 2 and 1? No, it's not.
So therefore, it wouldn't be super
Right.
increasing.
The 9's bigger than all the ones prior to it, but the 13 is not bigger than the 9 and the 5 and the 2.
Okay.
And the whole problem with that is that means there might be 2 answers for the same problem. We don't want that. On your homework assignment, it'd be nice if, I'm looking for one answer. And if there's 2 different answers that work, and you don't guess the one I want, you get it wrong. So that would suck for you. So I had to make sure they all worked correctly. And this is I don't know, if you went back and watched a couple years ago recording, it was funny because Grant Cadis used to work here. He used to work upstairs in our lab area. Okay? And he took my class. And he came out with this ingenious way of figuring out a number that worked. Because they had to write a program back then to do this one. Okay? But it was funny. His program worked perfectly for one set of numbers. If you change the numbers, it didn't work. So Because it was funny, he turned in, he goes, this is great, it worked. And it did, it worked great. So I said, let's try it with this. And it didn't work. And we're like, that sucks. I mean, what? No, it wasn't good. But no, Grant actually went to Tulsa, went to work for the NSA, and now he works at Dell, believe it or not.
Really?
Yes, yeah. But he works at Dell Austin. He's like one of the very head of their finding vulnerabilities in their whole forensic system. Yeah, enough money that it probably starts with 100 something. So. But it was just funny because his program was great. And I talk about him later on. He came up with another thing for calculating the inverse of W, and he's like, this works great. I said, yeah, for that one number. I mean, if you change the numbers, it doesn't work so well. It was just funny that worked that way. All right. Okay, everybody okay on what we're doing so far? Getting off a little early tonight. There's no new homework, so start working on the index of coincidence. Okay, you don't have to write a program, okay? You can just use Word. It's literally selected and it'll tell you how many A's, okay? I think if you go under replace and type in an A and it says, 285 instances of it, and you're like, sweet, there's all the A's. But you get extra credit if you write a program for it. And if you have a good program, the first homework assignment, the Caesar cipher, you're doing one of those on the test. So if you have a program that works great, you take test question, put in program, guess what? You got the answer in 2 seconds. So if you write a program to solve the index of coincidence, and you take a test question, you put in the question, boom, there's the answer. You understand how that might be beneficial to you? And I just try to make you guys remember something you learned before. It's kind of like, when you ride a bike, you always remember, well, you should do the same with programming. So,
Fun photos.
this is much more fun. All right. That's the end of that lecture and the end of this recording.